Hey, alright, so let's continue where we left off. We're still in chapter 20, which is the chemistry of carboxylic acid derivatives. And we were talking about amides. And the particularly we're talking about the reduction of them, which was C, reduction of amides. And what we found was that we could do this kind of two ways: the H-2 equivalent way and the H-1 equivalent way. So let me show, I'm not going to show the full mechanisms of those, but let's just give an example. I'll draw an amide. This is a cyclic amide, that's a methyl. And the H-2 equivalent way was lithium aluminum hydride. It's just the super reducing agent that we use for a lot of kind of difficult reductions. Anyway, lithium aluminum hydride and maybe H2O or H3O will reduce this. And what was weird about an amide reduction was that H- would attack the carbonyl, and then rather than you know, what we've seen a bunch of times now, like a nucleophile attacks, electrons go up, electrons go down, and off goes nitrogen. Rather than that, what we found is that the H- attacks, and then the nitrogen kicks off the oxygen. So without doing the full mechanism, I'll just kind of draw that part. H- attacks. We did the full mechanism last time. There's the H, and there we have the nitrogen. Yeah, and what happens is and then there's something on the oxygen. I just say X2 aluminum or something. It's something related to the other hydrogens, and there's lithium on there. But not, you know, AlX2. But that's a leaving group, and nitrogen kicks it off like that. And now you have this iminium plus charge on nitrogen, and then H- attacks that again. Okay, so that's basically what I showed last time in terms of the double reduction of an amide to an amine. Okay, and what happens with one equivalent, H- 1 equivalent, which is like dibol, is kind of the more conventional reduction where the H attacks, electrons go up, electrons go down, and then the nitrogen kicks off. I'll show that briefly also. Okay, so I'll even do it on the same substrate. So dibol we just kind of associate with like single step reductions or H- 1 equivalent. Okay, H3O or H2O. What happens is you get the aldehyde out, and like the amine, so it does a single step reduction. H- attacks. Okay, we did this last time, so I'm going to abbreviate it. the big thing though when diol attacks carbon, 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 is that, and then the aluminum with its two isobutyls looks kind of like Al, I'm going to call it Y2, you know, but the Y groups are isobutals, because above was X2, now it's Y2, I don't know. Of course, what the structure is, I'll draw over here. That's like those are Y groups for the isobutyls, Al, Y2. Okay, but in this case, like we always say for diol, this is a temporarily stabilized tetrahedral intermediate. Okay, and so nothing happens. Nothing happens. It just stops. It stops here until H3O is added. Okay, and and so you know, why is this temporarily stabilized? I don't have a good answer for that. I don't. Something about diol and the two isobutals and the electronics around aluminum somehow causes this to not get kicked off as a leaving group by either nitrogen doesn't kick it off, and nor does oxygen swing down and kick off the nitrogen. So this is just stabilized until H3O is added as a second step. Okay. And another thing about that is, you know, what does H3O do? Well, there's two things it does. I forgot to mention the second thing last time. It does two things. The first is it destroys excess diol. It destroys excess H minus. Okay. You can imagine what does H minus do when it sees H plus? It forms H2. So I'm just going to abbreviate that and say, oh, it makes H2. It destroys any leftover H minus. The second thing it does is oxygen grabs a proton from H3O. So now you have your normal tetrahedral intermediate. This probably also gets protonated because it's nitrogen, right? So now we have that. Actually, yeah, that's right. Yeah, plus charge. Okay. So yeah, and now you can see how easily this falls apart. It kicks off the nitrogen, and then you lose a proton of oxygen. So we have to do minus H plus here. And now you see the final product. Okay, so that's pretty cool, and that's how diol works. Kind of the same way that when diol reacted with esters, it did a partial reduction. Also, how it works when diol reduces amides to do a partial reduction. In a bit, we'll show how it works to do the same thing with nitriles. Nitriles also get reduced the same kind of way through a partial reduction. Okay. All right. Cool. Alright, so let's just show a couple examples of amide reduction. Let me see. Let's do a random molecule. Remember, ethers are generally non-reactive to most things, so this isn't going to get touched by anything. But what does lithium aluminum hydride H2O or H3O do? That, as we learned, it just does a double step reduction of the carbonyl, wipes it off the molecule. And you get the secondary amine, right? Ether is not touched. This is kind of a funny molecule. It's a sort of cyclic diamide. What happens when we do the same thing? The carbonyls get lost. And you get that. Okay, double step reduction. Double step reduction. Okay. Let's just see. What if, is there a way to take a carboxylic acid and reduce it to a aldehyde? Question mark. Have you learned that? I mean, we have learned that a carboxylic acid can be completely reduced to a alcohol, a primary alcohol. So you did learn that. But is there any way to convert a carboxylic acid to an aldehyde? And how would you do the reduction to an alcohol? You would just use your super duper reducing agent. Lithium aluminum hydride would totally reduce to the alcohol. But how do you get an aldehyde? Is this a possible reaction? And the question is, or the answer is, not directly. There is not a direct way to just magically convert a carboxylic acid to an aldehyde. Okay, but we do know a couple indirect methods. So, what's one of them? Well, we do know we can completely reduce the carboxylic acid to an alcohol using lithium aluminum hydride, right? Okay, well then how do we oxidize this back up to a aldehyde? That is the PCC. So that's organic 1 stuff. It's a single step oxidation from an alcohol to an aldehyde. Okay? Are there any other ways now that we know a little bit more about this? The stuff. How else could we go and do this? This is a 2-step process. Any other methods we could use? Well, I could envision another way. Now, we just learned of a new way that makes aldehydes, but from amides, right? Or esters, and it's using dibol. So we could say, make ester or amide, make an ester or an amide, your choice. You could do methyl ester or a methyl amide or something, and then we could do a single step reduction of the ester or amide using dibol and H3O. Okay, so now we learned that esters or amides are a single step reduced with dibol to the aldehyde. Okay? Any other ways? Thinking back maybe a tiny bit more, maybe earlier in this chapter. Other ways to do a partial reduction of something that gives you an aldehyde. This is a partial reduction of an ester or amide. Any other partially reducible functional groups? And the answer was SOCl2 makes a what? Acid chloride, right? And we also learned there's a partial reduction of an acid chloride, but it was not using dibol. They used a funny, different reducing agent that was something like this, ALH, tri-tert-butoxy. There's 3 tert-butoxy groups, aluminum hydride, tri-tert-butoxy, aluminum hydride, and that converts an acid chloride to an aldehyde, and that was H3O. Okay, so we learned that also. How do you keep track of all these partial reducing agents and kind of like when R minus, you can do R minus 1 equivalent or R minus 2 equivalents. I put something on the website. I'm just going to shoot the camcorder at it. It's on one of the forums because you're going to see this, and I just want to mention it real quick. 1 sec. This is on the. I don't know if you can see it. This is on the discussion forum. But yeah, like there's the acid chloride reaction, and there's a couple of things we can do. R minus 2 equivalent, R minus 1 equivalent, H minus 2 equivalent, H minus 1 equivalent, and those are the products. Esters and amides are kind of similar, except you can't. Oh yeah, with acid chlorides, there's the second one. I can't really point at it. The second one is a cuprate, right? So cuprate adds once to an acid chloride to make a ketone. esters and amides, you can do R-2 equivalents of an ester to make a tertiary alcohol. You can't do R-1 equivalent, but then H-2 equivalents you can do lithium aluminum hydride, H-1 equivalent diol. For amides, you have not learned any R- stuff. You have learned the H- things. Lithium aluminum hydride for 2 equivalents, diol is 1 equivalent. Okay, and then we're going to see something like this for nitriles too in a second. R-1 equivalent to make something a ketone. Those are nitrile, CN. And then there's also H-2 equivalent and 1 equivalent with diol. So we'll see that in a second. Okay, that probably wasn't the most clear way to show this, but I think it might be a little bit helpful for us. I would definitely recommend taking a good look at that handout and maybe print it out and put it in your notes or something. Okay? All right. All right, so next we're going to do a pretty cool reaction, and this is one of the weirder reactions in organic too. Always exciting, huh? Number 8, which is degradation of primary amides. And this is the Hofmann rearrangement. Hofmann rearrangement reaction. Hofmann rearrangement reaction. Okay, it's a kind of a weird reaction and fun mechanism, so always exciting when we have a different type of mechanism. Okay, and so what is it? What's the basic idea? The basic idea is that if you have an amide, is a primary amide, let's draw it a little nicer. NH2, right? Okay, there's a primary amide. What we're going to do is react this with Br2, NaOH, and water. Br2, NaOH, and water. And what's going to happen is, because how many carbons do we have here? Looks like we have 3, right? 1, 2, 3. 1, 2, 3. What's going to happen is we're going to lose a carbon and make a 2-carbon amine. That's weird. Right off the bat, that seems weird, right? How could you go from 3 carbons to 2 carbons? The other byproduct is CO2. Okay, and how does this work? Well, that's a great question for a mechanism. Great mechanistic question, right? How do we go from a 3-carbon molecule to a 2-carbon molecule? And then obviously CO2 is being formed, so that's another question of how that works. Well, let's draw a mechanism. Okay. And also, what do you think this might be called if we're losing a single carbon? It's called a 1-carbon degradation. 1C degradation. 1-carbon degradation. You might have remembered what it's called if we add a carbon. So if we add a carbon, it's not called a degradation, that's called a homologation. So versus homologation. Homologation, H-O-M-O-L-O-G-A-T-I-O-N, homologation. That's the opposite, that's when you add a carbon. Okay, so what do you think happens? Well, OH minus is a base. OH minus is a base, and what do bases do? Bases take protons, and we're going to use hydroxide as a base. Hydroxide's a base, so we're going to grab a proton and push electrons onto nitrogen. Okay. Okay, so simply grab a proton. Now we've taken a proton off, and we have a negatively charged nitrogen. Okay. Now, negatively charged nitrogen is going to attack Br, and Br is an electrophile, so Br can be attacked. So simply attack, and we've brominated the nitrogen. Brominate the nitrogen. Nothing too weird yet, right? Nothing too weird yet has happened. Okay, now we're going to react with OH minus again and do it again. OH minus is going to grab the second proton. OH minus grabs the second proton. Okay. Am I missing anything? Well, when the base takes that second proton, there's a charge left over. Negative. There's a negative charge on the nitrogen. Okay. This is where it gets a little weird. This is where the mechanism gets a little bit weird. So when you have this thing, it's kind of like we have a leaving group on a negatively charged atom. Leaving group, negatively charged atom. When you have this situation, which you've never seen before, a leaving group on a negatively charged atom, the leaving group just departs. So that's actually not that weird. What was weird will happen next, and I'm going to kind of go downward here just for space. Okay. So we have that. It's nitrogen with nothing on it except the carbonyl. Okay. This has a funny name. It's called a nitrene. Okay, so the nitrene is this, and is there a charge? Well, it shouldn't be, because we had a negatively charged nitrogen, leaving group went away, and now the leaving group's gone, so now you have a nitrene, and so now you have this thing with the nitrogen and the two lone pairs. So what is it going to happen next? It gets weird. It gets a little weird. This is maybe one of the weirder steps in the mechanism. So what happens here is circle lone pair, nitrogen, it just kicks in, and that forms a double bond, right? It's going to form a double bond to the carbon. Okay? And then the maybe weirder thing happens. We're going to circle this bond and have it jump. Yeah, that's kind of weird. That's kind of an unusual thing there, right? And you probably have to practice that a couple times. What does that give us? Well, it looks like now we have oxygen, carbon, double bond, nitrogen, two carbons. Now we at least see nitrogen, two carbons that we're going to see in the product, right? Nitrogen, two carbons. Okay. At this point, it gets maybe more straightforward. I'm going to abbreviate the following steps because they're not that crazy. This thing is called an isocyanate. That's the name of that intermediate, isocyanate. It's called a nitrene. This is called an isocyanate. Okay, and now if we go back to the mechanism, it's water, right? We have water around. Water is going to be a nucleophile. Okay, water is going to be a nucleophile, and attack and push onto nitrogen. Water is going to attack and push onto nitrogen. I'm going to add a PT in there so that when the water attacks and pushes onto nitrogen, the nitrogen gets one of the protons from water. So I just kind of, what we're going to get now is H. Okay, so I'm being I'm abbreviating a little bit there, yeah. Nitrogen, 2 carbons, and this oxygen, and it looks like a carboxylic acid on the nitrogen, yeah. This has a name too, so there's names for all these intermediates. This one is, I'm going to draw over here, carbamic acid. Okay, so carbamic acid, C-A-R-B-A-M-I-C acid. When you do this on your notes, you should make this larger and spread it out. I don't have too much space, okay? But the carbamic acid now, they are unstable. Carbamic acids are unstable, and you can see it almost looks like CO2 there. We have a carbon and the double bond O and the single bond O. This kind of is looking like it wants to form CO2, and it does, and that's the end of the mechanism. So the oxygen kicks in, breaks off onto nitrogen, and I also just write PT on there to suggest that CO2 is losing a proton as it forms, and nitrogen's gaining a proton, but the byproduct CO2, which of course we're drawing it there also, that is kind of how CO2 is forming, right? Very briefly again, the overall mechanism. The overall mechanism was base took the proton off nitrogen to make an N-. N- gets brominated, Br2. Then base takes off the other proton. You make this weird thing. It does not have a name that I know of, but you have an N- with a Br on it, a good leaving group. And now the leaving group goes away, you make the nitrene. The nitrene does the crazy thing. It's the rearrangement, right? Let's zoom in on there. So the nitrogen lone pair kicks in. The ethyl group jumps across to the other side to where the nitrogen is. Why does it happen? Nitrenes have very weird chemistry. That's why it happens. Okay. And then then water attacks the carbonyl and then pushes onto nitrogen. Just write PT while you're doing that, because PT happens also. And now you have the carbamic acid. Carbamic acid's unstable, degrades, oxygen kicks in, breaks off, and essentially gives you now, after all is said and done, a ethyl amine and a CO2. Okay, one more thing about this crazy mechanism. There it is, all zoomed out. The other crazy thing about this mechanism, the book actually does it a little differently, where it does a couple things simultaneously. I think the loss of the leaving group, the kicking in of the nitrogen, and the jumping, it does all of that at the same time. That is acceptable and may even be a little more correct, but I like to do this stepwise. I like to show this all as a kind of a stepwise process. As a mechanism, I think it's easier to follow if you do it as a couple steps. Okay? Loss of leaving group, rearrangement of nitrene, and then you have the isocyanate, and then the water attacks it, and then degrades, carbamic acid degrades to lose CO2. Okay. Okay, so let's just show a couple examples of this Hofmann degradation reaction example. What are the reagents? It's NaOH, Br2, and water. Hofmann degradation. I should point out again that this has to be a primary amide. Primary amide. By primary amide, I mean it has to be NH2 on the amide. So if you have like a carbon or something else on the nitrogen, it doesn't work. Okay. All right. So very simply, what's the product of this? Well, the carbonyl just jumps away. It gets lost. I mean, the mechanism is not that way, but the carbonyl gets lost, and then this carbon gets connected to NH2. So it's really just that. Lose a carbon, right? Plus CO2. So CO2 gets lost as a byproduct. Okay. Another one. Interestingly, I think if you do this on a chiral substrate and knowing the mechanism is kind of weird with all those bonds jumping around, and right, it makes the nitrene, and then the bond jumps across to the nitrogen. Remember that? Well, through all of that, if there is stereochemistry, like this is a chiral CH3, right? There's a star there for chirality. Well, that doesn't get messed up. You'd think that maybe, well, I generally think of chirality as something that can be lost, right? You could lose the absolute chirality of this, but it doesn't happen. The chirality is maintained through this kind of crazy reaction. Okay. All right, so let's get into chemistry of nitriles now. So we're done with amides and esters, and let's talk about nitriles a bit. We'll say that, they look a little weird in terms, are they really a carboxylic acid derivative? Well, they're the same oxidation state as a carboxylic acid. Carboxylic acids have 3 bonds to oxygen, these have 3 bonds to nitrogen. So they're kind of in the same group, and we just call them like a different carboxylic acid derivative. So different class of carboxylic acid derivatives. How do you make a nitrile? Well, we've seen it since organic 1. One is by SN2 reaction. SN2 is really easy to make a nitrile, so have something with a leaving group, usually primary or secondary, and we treat this with like Na plus, Cn minus, NaCN, right? Maybe a good SN2 solvent. What's a good SN2 solvent? Maybe a little DMF or DMSO or acetone. All of those are pretty good SN2 solvents. Polar aprotic, remember that? Polar aprotic. In organic 1, we explain why polar aprotic facilitate SN2 reactions. But this is an incredibly easy reaction. Cn minus kicks off the Br. Now we have a nitrile, right? So, and like we just said, when you lose a carbon, it's called a degradation, right? What was it called if you're adding a carbon? It's a C triple bond N. It looks a little funny, but there's 3 bonds there. This is a 1 carbon homologation. So those words are used, degradation and homologation, anytime we lose a carbon or add, we lose a carbon or add a carbon, we call it degradation or homologation. Alright, what's the other way to make a nitrile? We did mention this, I think, in maybe chapter 17. Cyanohydrin. Cyanohydrin is just a different kind of nitrile. So, yeah, I think this is chapter 17. And HCN can be used, or you can use NaCN and like H plus or something like that. Essentially, whoa, I messed up. It's a aldehyde or ketone. We'll do an aldehyde. Okay, so yeah, it's going to be an aldehyde or ketone, HCN, and then you make kind of like the alcohol derivative with an extra CN on there. And it sort of acts like a Grignard. I mean, you could maybe say it vaguely looks like a Grignard, right? Protonate the aldehyde. It's an RSCC, which you could draw if you like. But then CN minus just text. So that's a really straightforward mechanism to convert a ketone or aldehyde to this thing called a cyanohydrin. Okay, so we know we got the SN2 method to make nitriles. We have the sort of cyanohydrin method to also make nitriles. It's a nitrile connected to an alcohol. So hydrolysis. Hydrolysis is a reaction of a nitrile, and we have learned this extensively already. H plus or OH minus. I think it was on one of the quizzes or some, we've seen it recently. And hydrolysis of a nitrile gives a carboxylic acid and NH3. It's a long-ish mechanism where the nitrile gets protonated and then you make an RSCC, water attacks, and etc., etc. I'm not going to review that because we just learned it. It's in the book and it's in your recent notes. But hydrolysis is one of the things that you can do. Say a reaction of nitriles. Another reaction of a nitrile is with Grignards. And this is a little bit weird, but it makes ketones. How does reaction of a nitrile with a Grignard make a ketone? Well, and we're going to call this R minus 1 equivalent too, because it only adds once and we get a ketone. Let's just show it how it works. It's pretty straightforward. How about we react with a benzene, phenyl ketone, phenyl Grignard, and then we're going to use H3O as our second step. Net result, got a ketone now. And you're going to make some NH3 as a byproduct of this. Well, the mechanism is really easy. So all we do is have the benzene, Grignard, phenyl Grignard, attack and push electrons onto nitrile. Just like any other Grignard reaction, which usually attacks like a ketone, aldehyde, ester, etc. The Grignard attacks the carbon, kicks electrons onto nitrogen. And what does that give you? Kind of a protonated nitrogen, right? There's two lone pairs. There was one lone pair, now there's two lone pairs. Okay, it stops here. It stops, it doesn't react again. You can imagine it might react again, but it doesn't. I've never seen that happen. But now nitrogen, then you do your protonation with acid water. And it protonates twice. So nitrogen attacks, nitrogen protonates twice. Now it went from N- to N+. And there's a couple steps here. You should practice them. I'm not going to do it because it's old chapter, probably 17 stuff. But now we've seen this kind of mechanism probably 20 times. But yeah, now water attacks, proton transfer, make a good leaving group, and then oxygen kicks it off, and then you lose nitrogen. So you should be able to step through this mechanism. If you need help on it, come to office hours, and I can Zoom office hours, and I can step through it. Okay? But yeah, this is straightforward. Water attacks, proton transfer, make nitrogen good leaving group, oxygen kicks off the good leaving group, and then you have the ketone. So this is a great way to make ketones. A great way is to actually make a nitrile, which you can do by adding a carbon, and then Grignards attack nitriles to make ketones. Pretty cool. I'll show just another example of it real quick. This is kind of phrased in a synthesis type manner. How would you accomplish this? Well, we know now how to make ketones by kind of addition of something to a nitrile, maybe addition of isopropyl Grignard to a nitrile. And then we also know how to convert bromides into nitriles. So this is really straightforward. Now we just imagine and then NaCN, DMF or something like that, which will attack this. But what is the way to convert this nitrile to an isopropyl ketone? Well, just throw in isopropyl Grignard. And you're done, you got it. So that was a pretty easy way to go from a bromide to an isopropyl ketone. Okay. Okay, so still talking about nitriles. Next reactions, reduction. So reduction of nitriles. Just like we've kind of seen in all the recent functional groups, most of them at least, we're going to have two methods, H minus 2 equivalent and H minus 1 equivalent. And the 2 equivalent method will make amines. The 1 equivalent method to reduce the nitrile will make an aldehyde, which is a little weird given, you know, the nitrile has nitrogens on it. Where's the oxygen going to come from to make an aldehyde? Well, we'll see. What do you think the 2 equivalent reducing agent is going to be, and what do you think the 1 equivalent reducing agent is going to be? So generally, the super strong reducing agent we've seen is lithium aluminum hydride. Lithium aluminum hydride. For 1 equivalent, we've seen a couple, but the main one recently is dibol. So dibol or diba is the 1 equivalent reducing agent. Okay. All right. So let's show these two: H minus 2 equivalent first, and then H minus 1 equivalent. So for the double reduction, 2EQ, we're going to add 2 H's. Let's draw, why not a kind of complicated looking nitrile with a chiral center. What's the reagent for 2 equivalent? Oh yes, lithium aluminum hydride. Lithium aluminum hydride, H2O or H3O will work. And what's going to happen is that we're going to get a double reduction of the nitrile to which functional group? To an amine. And so I'll draw the product first, a primary amine. So primary amine, N with one thing on it, and we add 2 H's. What are the two H's? There are the 2 H's that we're adding in this process, and then the NH2 protons come from water. So how does it work? Well, it's just like always. We have nucleophilic hydride, Nucleophilic hydride is going to do what to our thing that has a delta minus and a delta plus? Well, H minus is going to attack H plus, C plus. So that makes sense, that the H would attack the carbon and push onto nitrogen. We had 1 lone pair. Now how many lone pairs do we have? 2. Okay. So yeah, that's what we got. Now H minus just does it again. And okay, H minus does it again. We have our 2 H's. What does nitrogen look like now? H minus attacked carbon and pushed onto nitrogen. This must look really weird because we had 2 lone pairs. Now how many do we have? 3 lone pairs on nitrogen. That's weird. What do you think the charge on nitrogen will be? The charge on nitrogen now, it was -1, now it's -2. So we say 2 minus. It's doubly negative, which is weird. And what's the formula for formal charge? It's a valence minus dots minus dashes. Remember that? Well, 5 5 valence electrons around nitrogen, minus 6 dots, minus 1 dash. So that's 5 minus 7 is -2. Yeah, right? So that makes sense that we get -2. Okay, then we just protonate H3O. Simply just protonates the nitrogen twice. So we protonate once, we protonate twice, and we're left with the amine. And that is the two-step, we'll say double reduction of a nitrile. Okay, great. Okay, so that's the one-step reduction, sorry, the two-step reduction, H-2 equivalent. What is the one-step reduction, and what's the final functional group? Well, we said it was going to be an aldehyde, right? And we're going to use dibol or diba. Let's show that. It's really easy, actually. Given what we've learned already, this is actually really pretty straightforward. So H-1 equivalent now is going to be the conversion of a nitrile to the aldehyde. So let's just do this one. Dibol H3O plus or H2O. Okay. And dibol is just a special hydride reagent. And it's just a different H minus, right? That stops halfway. And so the H attacks you get this intermediate. We're just going to call it, this is not a tetrahedral intermediate, but it does get stabilized the same way that what we saw before, the temporarily stabilized tetrahedral intermediates, which we saw with amides and esters. It gets stabilized the same way. So I'm just going to just write temporarily stabilized. Okay. So protonate it. Well, yeah, just like always, it's temporarily stabilized until the acid or water comes along. The acid or water will destroy the remaining reducing agent. So H minus, any excess H minus you got will get destroyed when we add protons or acid. And so this destroys the reducing agent. I just say it makes N2, right? Sorry, H2. It makes H2, degrades and makes H2. But then to your molecule, it's just going to protonate a couple times, and then water attacks. Okay, and it's the same kind of thing. Water attacks, electrons, proton transfer, etc., and then you're left with the aldehyde in this case. So the one-step reduction of a nitrile will give you the aldehyde, kind of through H minus attack, make a temporarily stabilized intermediate, negative positive. Acid will cause degradation of the reducing agent. H minus attacks H plus, and then water attacks proton transfer, make a good leaving group, kick off, and what's our byproduct here? It's an H3. So there you go. That's the H-1 equivalent reduction of a nitrile with dibol. Okay, and I want to just reiterate the really the cool slide on the iLearn site that shows all the different R minus 1 and 2 equivalent reactions and all the H minus 1 and 2 equivalent reactions for esters, amides, nitriles. What else? I think there's one more. Acid chlorides. And for H minus 1 equivalent reactions, I just want to point out again that if you have an acid chloride, the reagent is different. It's not dibol. It's HAlO3. It's tri-tert-butoxy. It's 3 tert-butoxys. Tri-tert-butoxy aluminum hydride to give an aldehyde. Whereas if it's an amide, an ester, or a nitrile, then we do a different one, and that gives you aldehydes. What is that? That's dibol. Okay, so yeah, we have like kind of like a different versions of these H minus 1 equivalent reagents. For acid chlorides, it's tri-tert-butoxy aluminum hydride. For esters, amides, and nitriles, it's dibol or dibol. Cool. Alright, so we're done with the last chapter. Chapter 20, we're on to chapter 21 now, amines, and like a lot of these functional group chapters, we are going to start off with some conceptual points about the about amines as a functional group. So amines are commonly found in a lot of pharmacologically active substances. Nicotine, cocaine has a kind of weird nitrogen ring system above here. Quinine, which is found in tonic water, and it's also anti-malarial. It has a kind of weird structure with a quinoline heterocycle on the bottom, the benzene and the nitrogen with a 6-member ring, and also this other nitrogen. And this is, again, anti-malarial. It's sort of the basis for a lot of other anti-malarial drugs like chloroquine and mefloquine and hydroxychloroquine, which you've heard about maybe recently related to COVID-19. Fluoxetine and antidepressants are often contain nitrogens, amines, amine functional group. Fluoxetine is also racemic. It has a chiral center, so this little squiggly line means racemic. And it is, as far as I know, they still deliver it racemic, and I don't think the chiral center actually improves its potency or activity. It might affect its metabolism, though. There's something about that chiral center. Let's see, the morphine-like alkaloids look like this. So we have a couple ring systems, and there's this weird bridged thing, carbon-carbon to the nitrogen here. Morphine has OHOH, like a dialcohol. Codeine has one of them be a CH3, a methyl ether. And what else? Oh yeah, the diacetylmorphine is what's known as heroin. It's a pretty major drug of abuse, but that has 2 acetyl groups, and that kind of enhances its bioavailability. So I think that's why it's used, I guess, as a opioid of abuse. All right. Imipramine is one of these other antidepressant type drugs. It's called a tricyclic antidepressant. Probably pretty clear why they call it a tricyclic antidepressant, because you have the 3 rings, right? And so this has a lot of the same effects as fluoxetine or Prozac. Amines are used as neurotransmitters in our body. So these are we'll say molecules that our body produces to transmit neural signals, serotonin or 5-hydroxytryptamine. Tryptamine, which is just kind of this bottom part and the 2 carbons and nitrogen, that would be tryptamine, which is related to tryptophan, the amino acid, but this has a 5-hydroxy group, and that's what makes it a neurotransmitter.
Epinephrine or adrenaline is a benzene, 2 carbons, and a nitrogen, a couple other things. Norepinephrine is the same thing, except it has the lack of the methyl group, noradrenaline. Acetylcholine is this molecule with a positively charged nitrogen in it. And glutamic acid is an amino acid, but it's also used as a neurotransmitter in our body. Gamma aminobutyric acid, GABA, is also a different neurotransmitter. So there's about 10 different molecules in the mammalian nervous system that are used as neurotransmitters. This is very brief neurobiology description of how in a neuron there's a little cleft in between a synapse and a dendrite, and little vesicles contain the neurotransmitters, which then kind of postsynaptically release their neurotransmitter, and then it gets transmitted to the dendrite, and that causes reaction with receptors on the other side, and then this is basically how neural signals propagate. Things like serotonin and I think norepinephrine, they after the neurotransmitters are used, it gets reuptaken into a new vesicle, and then it kind of recycles the process. And the certain antidepressants like Prozac, they block the reuptake process, which is why they're called SSRIs, a selective serotonin reuptake inhibitor. Amines have a categorization system, a little different than alcohols, but we have primary amines and secondary amines and tertiary amines and quaternary ammonium. This is called a quaternary ammonium, and the ammonium is the positively charged nitrogen. All right. How is this different from alcohols? Alcohols, it's when you're considering primary versus secondary versus tertiary, it's not like how many R groups are on the atom, like with the nitrogen. It's how many R groups are on the carbon where the alcohol is. So primary alcohol is you have one thing on that carbon. Secondary alcohol, you have 2 things on the carbon. Tertiary alcohol, you have 3 things on the carbon. Okay. Let's see. Amine naming is pretty straightforward for simple amines. Diethylamine should be 2 ethyls on an amine. Yep, that's pretty easy. Cyclohexane amine would be a cyclohexane connected to NH2. 1,4-butane diamine. Well, what do you think it is? Butane is 4 carbons. Then we have amines on 1 and 4. So it's this molecule. This has the lovely alternate name of putrescine. It's a lot of we'll say decaying body decay reactions and processes kind of produce this. And generally speaking, amines sort of stink. This one has a kind of lovely name, putrescine. They all actually kind of stink like that, though. I would say diethylamine stinks just as bad. But some of the amines have these alternate names or common names, like 1,5-pentane diamine, which is a pentane with 2 NH2s. It's this molecule. It also has the alternate name of cadaverine, so it's found in cadavers. Substitute amines. So 2-bromo-3-methylpentane amine. What do you think? Pentane is going to be 5 carbons nitrogen, and then 2-bromo into 3-methyl will be on the 2 carbon and the 3 carbon. So that's a pretty straightforward amine structure. NN-dimethylpropane amine. NN-dimethylpropane amine or NN-dimethylpropylamine. So I always look at the right side of the name first. Propylamine, 3 carbons nitrogen. NN-dimethyl would mean that we have methyls, 2 methyls on the amine. Okay. And so there we go. NN-dimethylpropylamine. R cis 3-pentene 2-amine. Well, if it has R, it's going to be stereochemistry. We're not testing you on R and S stereochemistry in this course. But this is a pretty complicated one. 3-pentene 2-amine. So 3-pentene 2-amine would probably mean 5 carbons, and then there's a amine on number 2, and an alkene on number 3. And then cis would refer to the cis stereochemistry on the alkene, and then R would refer to the stereochemistry on the 2-position amine. So this would be the molecule, and this is cis, and yep, there we go. 1, 2, 3, 4, 5, and this looks R to me. Yeah. N-ethyl N2-phenethylamine. Phenethylamine would be a benzene, 2 carbons, and a nitrogen. Benzene, 2 carbons, and a nitrogen, and N-ethyl would refer to the nitrogen having an ethyl group on it. Aromatic amines are also called anilines. So benzene with an NH2 is called an aniline. Okay, so this is a pretty easy one. And it should be distinguished from the amino acid alanine, which people sometimes mistake. That's alanine. It's an amino acid, one of the building blocks of proteins. 3-bromofour-methoxybenzene-amine. Well, benzene-amine will be the benzene with the NH2. 3-bromofour-methoxy should be pretty easy. 1, 2, 3, 4. We alphabetize the substituents, B before M. Para-aminobenzoic acid. Para-aminobenzoic acid. So benzoic acid is, of course, a benzene with the carboxylic acid. Para-amino would be a NH2 on the other side of it, and that's this molecule. And this is also it absorbs ultraviolet radiation, so it's what could it be used for? Maybe in our daily lives, and it's a sunscreen. So it looks like the sun's smiley face got burnt on the other guy's chest. Okay. All right, so nitrogens have 4 things around them, including the lone pair. So the lone pair is kind of like the 4th thing. And so it kind of has a tetrahedral type geometry, roughly about the same as a tetrahedral carbon. Being tetrahedral, the nitrogen could appear to be chiral, right? So it's weird that you can imagine nitrogen actually obtain chirality because it has 4 things around it, right? It's got ABC, and it's got the lone pair is the 4th thing. So that you could imagine these actually be enantiomers. And that is kind of true, except for a lot of cases, these things interconvert, and they don't actually hold on to chirality. But there are cases where it does retain chirality. I think I'll show in a second. So amines normally would equilibrate at normal temperatures. So therefore, you couldn't really hold on to a chiral center. Like a molecule couldn't stay chiral if it has 3 different things on it. The amines cannot. It's not like we could isolate this as a single enantiomer or this as a single enantiomer, because they have a very low energy of interconversion, which we show here. So with this kind of low energy conversion barrier at room temperature, these things go back and forth. However, in some chiral molecules, the nitrogen can serve as actually no. Let's look at this cocaine example again. So that in this case, when the ring has a nitrogen CH3, these things can interconvert, and we don't consider nitrogen a chiral center. This molecule does have carbon chiral centers, though, 4 of them. 1, 2, 3, 4. So that there are 4 carbon chiral centers, but the nitrogen we wouldn't consider a chiral center. Are there cases where nitrogen can be a chiral center? And the answer is yes. When a nitrogen is locked into multiple rings and cannot interconvert, then nitrogen can act as a chiral center. So yohimbine, which is a aphrodisiac purported molecule, actually has the nitrogen's locked in 3 rings, and this actually acts as a chiral center. But this also has carbon chiral centers. So this is kind of a trivial point here, that nitrogen is a chiral center. This is maybe a cooler example because it has no carbon chiral centers, right? There's no carbons with 4 things on them. So This does contain nitrogen chiral centers. These nitrogens act as chiral centers. So what could be a property of this? Well, if it's got these two nitrogen chiral centers, there could be two enantiomers where this CH2 thing could be poking towards us or poking away. And indeed, in 1887, this molecule was synthesized as a racemic mixture. In 1944, somebody was able to separate them into enantiomers, and then there are two enantiomers of this, with the CH2 coming towards us and the CH2 going away from us. Amines participate in hydrogen bonding, but not quite like alcohols. So they don't like to give away their protons, because the protons are very non-acidic. They don't like to give them away, but there is a little bit of hydrogen bonding, even though they're poor hydrogen bond donors. So the boiling points are typically lower than alcohols. If we consider methane versus like methanol, methanol is 65, and methylamine is kind of in between. So the amines have a sort of an in-between boiling point. Methylamine is also same kind of thing. If we compare methylamine, which is, I'm sorry, that's ethane. Ethane is -88, ethanol's 80. Ethylamine kind of in the middle, right? Okay. And also if we add R groups, diethylamine to triethylamine, so one ethyl is 16, two ethyls is 56, three ethyls is 90. So there's a kind of an increase as you add more R groups due to van der Waals interactions. Spectroscopy. How do we calculate degrees of unsaturation for nitrogen? Well, you better get used to it because you're going to see it on these upcoming quizzes. So remember the rule, nitrogen we subtract an H. So if we have an amine, we have to subtract an H before we do this calculation. This is sort of my calculation that I came up with for UN. Oxygens you ignore, halogens you add, nitrogens you subtract. Okay? So try to get these, try to do these. Look, see if you can do it. This should be easy for you. Look in Wikipedia for the answers. Well, also, you can, given the structure, which you can find on Wikipedia, you can confirm that it should be 8, 4, and 9. Okay, and so looking at the structures on Wikipedia and giving you the answers, if you cannot get these right answers, 8, 4, and 9, then you're not doing this right, and you should probably ask me, maybe in office hours. Okay, spectroscopy. Let's see what else. So this is methyl diethylamine. So we have a methyl group and two ethyl groups. The carbons next to nitrogens are shifted downfield a little bit, not as much as oxygen. Because where does oxygen come? Maybe as far as 4, right? If you have an oxygen, the neighboring atoms are around 3 or 4. In this case, the nitrogen doesn't pull them as far down, so it's kind of like 2.3 and like 2.6. So there's a little bit of a downfield shift, but not that much. Okay, and of course the quartet triplet indicates the ethyl group. This is the carbon. There's a little bit of a downfield shift in the carbon. So nitrogen is not as far downfield as oxygen. Where do they come if they're next to oxygen? Kind of in the 3 to 4 region, which is where our chart puts them. How about this molecule? Now we have a primary amine. So looking at it, 6 hydrogens are the 2 methyls. It's doublet because they're next to CH. We have this downfield of CH2, which is probably the NCH2. It's a triplet because there are 2 neighboring CHs. The NH2 is a broad singlet, around 2, and that varies. So this thing is the NH2. This goes all over the place, and it cannot be really predicted. So when you see a broad singlet, usually you think, oh yeah, it's the NH or the NH2 or whatever, right? Okay, and then this guy, the central CH is the CH right there. It's a multiplet split by 6, 7, 8. It's a no net 9. It should be 9. Little peaks because it's these 8 neighbors. Quartet here is this one, okay? Because it's these 3 neighbors plus 1 is a quartet. I should mention also, this one is a triplet. Why isn't it more than a triplet? Why isn't it like a pentet? If there's 2 here, 2 there, 4 plus 1 to be 5, why is it a triplet? Remember, the n+1 rule doesn't work, doesn't count neighboring NHs, okay? Oh yeah, also remember the rule that we'd often say, oh, it disappears at D2O. Like this would disappear at D2O because this can be hydrogen bound away and replaced with H's can be placed at deuteria, right? So this might disappear at D2O, and that's a trick to know, oh yeah, it's an NH or OH or something. So try this problem. I'm not going to do it for you. See if you can get the right answer. Here's a hint. Hint about amines. What does the integration of the 2.5 peak tell us? It's a broad singlet. There's 2 protons. So is it primary or secondary or tertiary amine? Let's also start with UN, of course. Oh, 2H is probably a primary amine because that could be an NH2. All right. So there you go. There's your substructure, NH2. See if you can do the rest of this. How about this one? Here we have another one. C6H15N. Start with the UN. Calculate the UN. 2 H's. What do you think? How many? Is it a primary, secondary, tertiary? Well, probably a primary because it's 2 H's, right? Should be a very easy molecule to solve the structure for. Okay, now this is interesting. It's a BS of 1H. So maybe that is it a primary or secondary or tertiary? Probably going to be a secondary amine. 2 things on it. You have 1 left over. It's an NH. See if you can do this problem. Don't be concerned by the downfield chemical shift of the broad singlet. So it's not significant. The fact that it's a 3.8 or 2.5, that doesn't mean anything. It's really just the integration and has the fact that there's a BS. Focus on the integration. Yeah. And it's a secondary amine. So now you know it's an NH with 2 things on it. So figure out the structure. Okay, basicity. There's 2 things. There's 2 concepts. Here, there's kind of one is like, why is LDA such a super base? We know it's a super strong base. It deprotonates ketones and esters. The other is like, this is actually a base too, but it's kind of a weak base. But we use triethylamine as kind of a mild base to just soak up protons. So this is extremely reactive, very strong base. Why is it? We'll review that. This is a moderate base, more so than a simple neutral organic molecule, but not as strong as LDA. So why do we have this? Why do we have that? That's what we got to answer, and then we'll be done with this PowerPoint. So amines are weak acids, and so the amine doesn't really want to give up its proton, like to water, for example. This is not that acidic. The pKa is 35, which is a huge number, right? So this is not a favorable reaction because this is not very stable, right? You always think with the stability of the conjugate base. So N- is not very stable, and so water is not going to readily rip off this proton. High pKa. Okay, so now we just explained why this is LDA with a lithium on it. Why is this such a strong base? It's because its conjugate acid has a high pKa, right? So how do we make LDA? The best way to make it is just start with diisopropylamine and use a super base like butyl lithium, which just rips off that proton and gives you LDA and makes butane, which is butane, right? And of course you go towards the higher pKa. So butane has pKa 50. Now you can see why this pushes forward to the right. As a neutral species, simple amines are relatively basic, or we'll say moderately basic. They take off, they find HCl and remove HCl and things like that. So propylamine, the pKa of HCl is -8. Propyl ammonium is pKa 9 or 10. Equilibrium goes towards the positive, larger pKa. So this equilibrium goes to the right, and it's just it's a mild base like that you'd use to like soak up HCl or something. Whereas an alcohol doesn't do that really, right? Or not as much. An alcohol is not that basic. And the way you know that is because you look at the pKa's. Of course, this pKa is 9 or 10. This is like 1 billion times less basic. So this reaction is not very favorable on the bottom. So that's why we say an amine is a little more basic, than an alcohol. or we actually, based on the pKa's, it's like a billion times more basic, right? More basic, less basic. Amines are more basic than alcohols because nitrogen is slightly more electropositive and can stabilize the negative charge. So yes, nitrogen is a little more electropositive. It's a little left on the periodic table, and can stabilize the positive charge just a little bit more. Okay, so here's the equilibrium. Amine, slight base. Oh, carboxylic acid. Well, yeah, you could predict that this is going to go to the right, and because you're going towards the larger pKa value. So this amine would readily deprotonate the carboxylic acid. Okay, what about a diisopropyl amine reacting with a ketone? pKa 20 versus pKa 10.1. While the equilibrium lies to the left, this is not strong enough of a base. That's why we don't use this as a base to deprotonate a ketone, right? Indeed, it might actually act as make an enamine, because it's a secondary amine, and secondary amines react with ketones to make enamines. The only thing that might prevent that is this is sterically hindered, the two isopropyl groups. But this is certainly not a strong enough base to deprotonate the ketone. Okay? What about this? Now we have LDA. LDA sees the ketone, it readily takes off the proton, and that's because we're going from 20 to 35. So this is kind of the normal use of LDA. Super duper basic, non-nucleophilic nitrogen, because the isopropyls decrease its nucleophilicity. And so this just rips off the proton and gives you an enolate, and then we can do all our enolate stuff, right? Aldols and, habitat things, alkylate the enolate, etc. Okay. I think this is the last slide. Anilines are a little less basic. So remember, if you did this without the benzene, I think the pK is like 9. Anilines are a little less basic, and why is that? Well, because the nitrogen has a lone pair. It's delocalized into the benzene, and so this is actually stabilized. This is very stabilized by resonance, and when it's stabilized, it's less reactive. It's less likely to go grab a proton. So this is not a high pKa thing. It can be a nucleophile, and it is a slight base. It's just not as basic as a normal amine. And that's due to all the resonance. Nitrogen lone pair is tied up and cannot form resonance structures. I think that might be it. More resonance stabilization. Less resonance stabilization. Okay. And yeah, that's the other thing, is you're going from something that's more resonance stabilized to something that's less resonance stabilized, because this doesn't have a lone pair that can kick in, and so this is not as happy. So you're going from something more happy to less happy, and that's another reason this is not very favorable, right? That's it. Chapter 20. What is this? 21, I guess. The conceptual items, and we'll get into the reactions and all that fun stuff for amines next time. All right, see ya.